Okay, so the first thing I think is just to make sure that during the test that you have a calculator. I would imagine that you're going to want one, ideally one that has distributions in it. If you have one that doesn't have distributions in it, that's okay. Like I'll put the tables on there, so like the normal table and the t-table, but I think getting values out of those tables is generally easier with a calculator. So if you've got one with distributions, I think that's really what you're going to want. All right, so first, section 5.1, I guess first being able to tell discrete and continuous random variables apart, which isn't really any different from just telling discrete and continuous variables in general apart. Basically, when that would have come up kind of early on in the class, it's the same sort of idea. So if that comes up, it's about the same. Then finding probabilities from a general discrete distribution, that's like when you have the table. So when you have the table where you have the possible values and you have their probabilities, and then you can figure out the probabilities of intervals from there. So by intervals, I just mean like probabilities that have inequalities in them, like the probability that x is greater than 2, or the probability that x is strictly between 1 and 6, or something like that. 5.2, the expected value and variance or standard deviation, I guess one or the other, right? I mean, if you can get the variance, you can get the standard deviation by taking the square root. But finding these things for a general discrete variable, so again, that's probably a situation where if you have to do it, the way that the distribution is going to be written out is probably going to be as a table. So the expected value is not too bad, right? Just by definition, that's a weighted average of the possible values where the probabilities are the weights. So you can kind of systematically go through it column by column to get there. And then the variance or standard deviation, you'd have to have the expected value first in order to do it. And then there are a couple of ways of handling that. One of those formulas, which would be the more conventional one to use, is actually in the formula sheet. The expected value formula is on the formula sheet as well. So I guess there, the best thing to do might be just to make sure that you're comfortable with how that's phrased on the formula sheet. So like the capital sigma means summation and that kind of stuff. And then mu is the same thing as the expected value, because I think, I don't have a printout in front of me, but I think that in the formula for the variance, it's just written as mu, not expected value of x. So just make sure that you know how those formulas are set up and that you're comfortable with them. That might really be the best thing. I would expect an expected value to be there. The variance, maybe, maybe not. I mean, it's a decent bit of computation to get one. I guess it depends on how long the test is. So that might happen, it might not happen, but that's one where I kind of have to make a definitive call on it later, I would think. 5.3, so now rather than general discrete variables, we get into a binomial distribution in particular, which is one where there are two possible outcomes to an event that's repeated multiple times. So let's see. As far as finding probabilities from a binomial distribution go, that'll be there, I'm sure, but I'm going to set it up to where it's one where if you didn't have a calculator with distributions in it, it wouldn't be one that would take that long. So it would probably be one where you'd really only have to get one binomial probability or maybe two in order to answer the question. It wouldn't be one where you'd have to get like 6 individual probabilities and add them up. That would put anybody who didn't have distributions in their calculator at a huge disadvantage. So that's not coming, but I would think like if you can do one or maybe just two and then add them together, that would probably cover it. And then the expected value and standard deviation or variance, I suppose, of a binomial distribution, probably just going to be expected value and standard deviation, which is why I wrote it like that. The general discrete formulas would work for the expected value and the variance, and then taking the square root to get the standard deviation. But there are those specific ones for a binomial that are way shorter, like that the expected value is n times p. That's a lot shorter. And then the variance is the square root of n times p times 1 minus p. So, or the standard deviation is the square root of n times p times 1 minus p. I think I just said variance. Those, I mean, I would use the shortcut there since it works 100% of the time, and it's like I don't know, 1/50th of the work, maybe something like that. So, yeah, if that comes up, expected value or standard deviation of a binomial, do it the short way rather than the long way. All right, chapter 6. 6.1 is more like an intro section. And the biggest things there, I think, are just the properties. So like properties of continuous distributions in general, which would be stuff like that you don't have probabilities for individual values, like you don't have the probability that x equals 4. Or, well, I guess you do, but the probability of any individual value is going to be 0. So rather than looking for those sorts of probabilities, what you really do is you look for the probability of an interval, where then graphically what that would correspond to would be the area under the curve. So that kind of thing is what I mean for properties of continuous distributions in general. Normal distribution, that's going to be stuff like, it's a bell shape, perfectly symmetric, centered at the mean, entirely, like a specific normal distribution is entirely designated by its mean and standard deviation. So that kind of stuff. 6.2, how to find probabilities from a standard normal distribution and how to find percentiles from a standard normal distribution. Okay, if you're going to use a calculator, so probabilities, that would be normal CDF. And then percentiles would be INV norm, because you have to use the inverse procedure to get a percentile as opposed to getting a probability. If you're going to use the table, you could do that too, right? The normal table is really a standard normal distribution. So using the table, like that's perfectly set up for it, where then you would just have to know how to figure out what row and column you're supposed to be in, right? So if you have like your standard score or your z-score, whatever you want to call that, then if you round it to 2 places, what's before the decimal point and then the first digit after will tell you the row to be in, and then the digit that's in the 100th place in the second place after the decimal point will tell you what column to be in. And you can use the table like that. And then for percentiles, you just find the closest value in the inner part of the table and then figure out the z-score that goes with that value. And you can get your percentile like that. Probably easier with a calculator if you've got one with distributions in it. 6.3, okay, so 6.3 is basically 6.2, but just applied to all normal distributions, not just a standard normal. So by all normal distributions, that just means like anything goes with your mean and standard deviation, right? So the way that I look at it is if you can do the stuff that's in 6.3, you would have to be able to do what's in 6.2, right? Because with 6.3, that's where you can have like all different means and standard deviations. So like if you can do that, then 6.2 is really just a special case of 6.3. It's the one that has the least amount of work as well. So yeah, if you can do 6.3, you could do 6.2. All right, 6.4, basically it's normal probability plots. So how one is created, I'm not going to ask you to make one from scratch. Like I'm not going to put that normal probability plot table on the test or anything. But just to know that basically it's you have the values from the sample on one axis and then values from a standard normal on the other axis. That's pretty much it. And then that they're plotted where like in order to get the points in the scatter plot, it's the 2 lowest values, so like the smallest value in your data set paired up with the smallest standard normal value, and then second smallest with second smallest and third smallest with third smallest, all the way up to largest with largest, and that's how they're made, right? That's how they're constructed. And then how to interpret one, basically you want it to look straight, right? The thing that you want it to look like it's a straight line. So you don't want to see any obvious curvature. You don't want to see those elbows or those sharp bends that you get if you have a data set that's skewed. So if it's straight, that means you've got a normally distributed sample. So then you could infer that it looks like the population is also normal, right? That's the thing that you're trying to get, right? That's ideally what's there. So basically, when you look at the normal probability plot, that's what you want to see. You want to see a straight line, no obvious curvature, no elbows, and ideally no outliers either. 7.1. It looks like this is kind of repetitive, but sampling error and sampling variability are different things, so I just kind of wanted to stress that here. So sampling error is the difference between your estimate, so like the value that you get from your sample, and then the population measure that you're trying to estimate. So like that would be the difference between like the X bar in your sample and then whatever mu actually is, right? So that's what sampling error is. Sampling variability is just that from one sample to another, you should get different values of X bar, right? Different samples are going to have different individuals in them. So you do expect things to change, right? Like whatever variable you're looking at, if you've got different individuals all of a sudden, you don't expect to get all the same measurements that you got in your first sample, right? So they are different ideas. So sampling variability is just how like X bar would vary from one sample to another, but then sampling error is the difference between X bar and mu. And then the relationship between sample size and either of those things, this is actually pretty similar. If the sample size gets bigger, both of those things become smaller. So a larger sample size, you should have less sampling error, meaning that your estimate of mu should be more precise. But also, you should have less sampling variability. Right? If you have bigger sample sizes, then yeah, different samples are going to give you different values of X bar, but like those X bar values aren't going to bounce around as much. So bigger sample size will make both of those things decrease, sampling error and sampling variability. 7.2, this is basically it, because the way that the sampling distribution was broken up in 7.2 and 7.3, it's got the mean standard deviation here and then the shape in the next one. So the mean is mu, standard deviation is sigma over the square root of n. Don't forget about that division by the square root of n. It's really easy to forget that. So if there's one thing to really watch for in this section, I would say that has to be it. 7.3, the central limit theorem is the big thing here. So knowing that just as the sample size increases, the sampling distribution will get closer and closer and closer to a normal distribution. And if your sample size is at least 30, then that's large enough to say that the sampling distribution should be approximately normal. And then if you have a large enough sample size for that, then you could find probabilities relating to the sampling distribution of X bar. That X bar looks really weird. Like, I don't know why the bar on top is so short, like why it doesn't go all the way across the X, but whatever. I guess PowerPoint doesn't like special characters. So yeah, right, if you have a big enough sample size, you could find probabilities that relate to the sampling distribution, or if the underlying distribution was normal, right? Because we had that come up too. So that's a possibility as well. And there you wouldn't even really need the central limit theorem, right? If the underlying distribution is normal, the sampling distribution has to be normal as well. So I guess that's the other case where you could find probabilities related to the sampling distribution. But mostly when we're talking about that, it's when you're in a situation where you have a large enough sample size to apply the central limit theorem. Chapter 8. So let's see. As far as finding confidence intervals in general, I can tell you what I think I would expect. I would expect the ones where sigma is not known. So like an 8.3, because that's the one that's the most realistic. Finding confidence intervals using the empirical rule, like you can do it. I'll freely admit I'm probably not going to put that on there. Maybe, but I'm leaning toward not including it and just saying if there's going to be a confidence interval computation, I'm going to make it the one like in section 8.3 with the t-distribution, because that's the one that's the most realistic. But, you know, I mean, it's just based on if you're going to use the empirical rule, the 1, 2, or 3 standard deviations away from the mean. The big thing in 8.1 is what's on the right side of the screen. So how to interpret a confidence interval. So and I know we've gone through it a lot. So I mean, I guess probably kind of obvious that this is the important part, but that you got to get the confidence level in there. obviously the interval endpoints, and then writing out the whole parameter where we had like that 3-step way of doing it with what type of number you have, which would have to be a mean, since that's all we've covered so far, and then what the population is, what the variable of interest is. And then the other thing with the interpretation is make sure you don't include any probability words because they don't really apply. Like that concept of probability in general doesn't really apply once you have all the numbers subbed in the formula for a confidence interval. 8.2, let's see. The biggest thing in 8.2 actually is going to be the thing on the left. So the assumptions for inference, where really we've got the first two are the big ones, right? Because there were the assumptions for inference in 8.2 and then in 8.3, and the difference between them is that third one where it's sigma known versus sigma not known. That's not like a big assumption or condition there. The first two, those are the big ones, right? So the first one is having a simple random sample, right? Or if it just says random sample, that's good enough. And then the second one is related to the sample size, right? Because the second one is, do you have like a little sample or an intermediate sample or a large sample? If you have a large sample, then you can just apply the central limit theorem and be done with it, and that'll take care of that assumption. Otherwise, you probably need to look at some stuff, right? Like if you have a really tiny sample, that's where we probably want to look at like the normal probability plot and a box plot. Because you want to make sure that it looks like your sample comes from a normal population, and you also want to make sure there are no outliers. That's what the box plot's for. Then the intermediate size, that's where maybe you could use a histogram instead of the normal probability plot. And if it's not perfect, that's okay, as long as it's like symmetric and single peaked and with no outliers. What's probably going to happen as far as those assumptions go is it's probably either going to be a large sample or it's going to be a tiny sample. That intermediate range, it's too subjective for a test, I think. Right? Like, I mean, it's an important thing, it comes up, but like on a test, it's just too hard to shoehorn that in and have it be something where there's a very clearly delineated right and wrong. So I would be thinking it's either going to be a big one or a little one on the test. That's the way that I'm thinking about how I'm going to write it. So that's, I think, what I would expect. Let's see, how to find critical values from a standard normal. I mean, it's good if you can do that, I think. And like with the calculator, it's INV norm. And then basically it's just like finding percentiles if you're using the table. I guess also if you're using a calculator. I don't know that you're going to need to do it because I'm probably not going to put a situation on the test where you'd be getting a confidence interval where sigma is known, just because that's not a realistic thing. What's going to happen instead? Probably this kind of confidence interval. So one where you don't know what sigma is because like in reality, that's the way it works. Right? Like you're not going to have sigma but not have mu when sigma has to be computed based on mu, right? That's kind of impossible. But that means that you'd have to use a t-distribution. So that I would definitely be familiar with. So like how to get a critical value from a t-distribution, either using a calculator where it's the INVT function, or how to do it with the table. And the properties of the t-distribution, let's see, I guess there's actually kind of a lot of that, right? Symmetric, centered at 0, bell shape, thicker tails than a standard normal. Let's see, the larger your sample size is, the thinner the tails are going to get, right? Or if you have a little sample size and you're going to have big, thick tails. The t-distribution, like the specific one that you need, is characterized by the degrees of freedom, which would be equal to the sample size minus 1. So there are a lot of t-distribution properties. I think that's really the big thing in 8.3, right? Because 8.2, like the way that our book is set up, it's almost like a bridge to get to 8.3, where in 8.2 you get used to, okay, this is how you actually do the computation for the confidence interval. And then in 8.3, it's basically we're just subbing in the t-distribution for the standard normal because we don't know what sigma is. So most of 8.3, I think, is just being comfortable with the t-distribution and knowing how to get the critical value if you need one. Right? Like if it was get a 99% confidence interval from mu, and it's a situation where you have S instead of sigma, then just knowing how to either get it using your calculator or how to get that critical value using the t-table, either way. And I think, yeah, that's it. So I have a bunch of notes over here, and I got all that stuff in here someplace. So it doesn't look like I missed anything, so that's good. But that's pretty much it. I think this one, it's harder material, but there's less of it, right? Like that first exam, there's a lot of stuff. Like there's a ton of stuff, like a lot of terminology, like there are a lot of little things there. So I guess it's sort of a trade-off in a way, right? This one has less stuff, but the stuff that's there, I think, is more difficult. But also there are a lot of things that kind of relate to each other on this test. So I think that ends up being a helpful thing ultimately. But that, I think, would cover all the topics that I would expect to be there on the exam on Thursday.